Hey everyone, and welcome back to Knowledge on Ears. Over here we have an LED connected to a 220 ohm resistor, and then we also have this infrared receiver which receives infrared light, and it's connected to my Arduino board, which is then hooked up to my laptop. My program, what it does is that when I press this power button on my remote, then my LED turns on, and when I press it again, it turns off, as you can see. So the receiver is receiving that infrared light from my remote. But that's only if I press the on button. If I press any other button, as you see, the receiver is still receiving the light, but it's not turning the LED on. So that's basically how it works. Let's jump into everything else. So in an infrared remote, when we press a button, let's just say we press the volume button, we're sending a certain signal to the receiver. The transmitter on our infrared remote is sending an infrared signal to our receiver. And depending on the different buttons you press, there's different signals. And these signals are in binary. So we know binaries are ones and zeros, there's two states. And so in this case, typically, for remotes, for infrared remotes, we have 32 bits, which are 32 ones and zeros. And so that's a lot of different combinations for a lot of different buttons. And so each of these individual combinations represents a certain command. But let's just say we have a remote and we're sending a signal from our transmitter to our receiver. There can be a problem that we face because right now we're talking about infrared light. And in our rooms all the time, there is so much different infrared light from our incandescent bulbs and our microwaves and our ovens. Those all emit infrared light, which is why that can be a problem. And this ambient sources of infrared light can actually act as noise, and it can jump in between, and it can actually transmit to the receiver, and it can give the receiver data that we never wanted to give the receiver. So that can be a problem, which is why we have these two different data encoding techniques, Pulse Width Modulation and Pulse Distance Modulation. And the reason these two are so good is because these two techniques make sure that we send this infrared light from our actual remote instead of extra noise. We send it at a certain fixed frequency. In most cases, it's 38 kilohertz. And this fixed frequency means that our receiver is also set at a fixed frequency. So any other infrared light, any other noise that is in our environment gets disregarded because we're only looking at 38 kilohertz, which is being sent by our transmitter. So now let's dive into these two different techniques. So we have Pulse Width Modulation, PWM. And what this means is that, let's just say we have a signal. Let's look at one single bit. So we've looked at pulse width modulation in our previous videos, like our servo motor video. Feel free to check that out. But basically, if we have a shorter pulse, that represents the bit of 0. If we have a longer pulse, that's the state of 1. So basically, the length of the pulse, the width of the pulse is what determines what bit we are looking at. So what state we're looking at, 0 or 1. Pretty simple. And as you can see, this time, the entire cycle time stays the same. You can see that the entire time is the same, no matter the distance or the width of the pulse. So this comes back to duty cycle, where we've actually gone over this in other videos, but the duty cycle is the percentage of the entire cycle that is on. So this would be a lower duty cycle percentage, this would be a higher one. Now, for the second one, pulse distance modulation. You can see the width and distance is changing between these two words. In this case, this is the exact opposite of pulse width modulation, where this time, the pulse times are the same. You don't change the pulse times. But in this case, the entire gap, the ending, the time it's off changes. So here, the cycle times are actually different this time. The pulse times are the same, but if you have a longer distance, a longer gap at the end, that represents the state of 1. Shorter gap represents the state of 0. But make sure between all of this is all 38 kilohertz. So it'll still continue to go on and off at 38 kilohertz, 38,000 cycles per second. But these separate different pulses and different cycles and different lengths of on and off is what makes our infrared receiver know that this is a signal being sent by the actual infrared remote. So yeah, we have pulse distance modulation changing the gap, and pulse width modulation changing the width of the actual on time. So this is changing the width of the off time, this is changing the width of the on time. Except the difference is this one has the same cycle length, this one has different cycle lengths. So yeah, in total we send like 32 of these normally. So that will give us one full command. Now let's go into a different experiment. So right here we have my Arduino board, it's connected to my laptop, and we have a program running where basically we have this infrared receiver, and whatever command we press on this remote, it's gonna give us our binary code on our Arduino serial monitor. So let's check that out. So if I start with the power button, I'm gonna press the power button. You can see how the second last one is the actual binary code. The 1111, like the one that has a lot of ones, that one is actually the code that gets spammed if you hold a button for too long. So if you don't click it very like sharp and once, then it'll give you the actual code, but if you hold it, it'll give you the one code. So let's do another one. Let's do the volume one. Once again, I held it for too long, so it printed the 1. If I do button 3, we get that one. So they're all different, and you can check that it goes up to 32 bits in total, so that's pretty cool. So I hope you enjoyed this video. It was very fun to make too. I hope you understood everything. Thank you so much for listening. Bye!